Nothing in my purse. Okay, let me see. This is my last lecture because unfortunately I have to travel, but you'll have the treat of having Yang Dong here to give the last two lectures, and he's really excited about Bayesian segmentation, so I think he'll do a very good job. But I did grade the exam, and for the off-campus people, I loaded the exam solutions or grades in FileLocker, and for the on-campus people, you can actually go to Bonnie or Sherry in MSE 330, and you can collect your exam with an ID. Okay, so you have to show an ID just to make sure that the person picking up the exam is the correct person. And now there was a fairly wide range on the exam. I don't want anybody to panic, okay, if you were on the lower end, okay. They sort of clustered because some of the problems were a bit all or nothing with the partial credit, okay. I didn't feel there was anybody who was like clueless, okay. Now one thing I have to honestly say I have to follow is the labs, okay? I'm expecting that there's only 3 labs in this class. 3. 1, 2, 3, okay? Anybody who wants to get an honorable grade in this class is expected to do all the labs, okay? I mean, that's not unreasonable, I feel, okay? Plus, you have next week is the final exam, and, this material, okay, I'll just say it. It's not going to be a focus of the final exam, okay? Okay? This is sort of extra material this week, okay? So there's some kind of thing going on. So you should have plenty of time to get the labs done, okay? Especially if you didn't do so well on the exam, okay? If you didn't do so well on the exam, you must do the labs for sure. And I'm sure the people who did do well on the exam will do the labs also, okay? So I expect that all labs will be done. And if you're like hitting some huge problem, you know the rule, come let me know, okay? There's only 3, 1, 2, 3 labs, okay? So do them. And if you have any problems, let me know. If you have any questions and you're getting stuck, email me, and sometimes I can answer it, but also I can also pass it on to some graduate students that work with me, and they can usually answer the questions too. So are there any questions then? So maybe we'll get on now to the last section, okay? Okay, so Bayesian segmentation, okay? So we're going to, so this last section is on Bayesian segmentation, and so the same kinds of things we talked about for mass estimation for restoration or reconstruction can be applied to problems in segmentation. So here what happens is that, let's say you have an image and it's got different textures. This is basically the material of Lab 3, which you've done, I assume, or working on, or at least intend to work on very soon, okay? Okay, so this is the different regions of different textures, and what happens is that if you associate with each region a label that's discrete, okay, say between 0 and 3, so there are 4 labels in this example, then estimating the label at each position is equivalent to segmenting the image, because you've separated the image into regions that are labeled, classified, all right? The difference between pixel classification and image segmentation is image segmentation is a spatial process in which you're really trying to account for spatial behavior as opposed to operating on individual pixels one at a time independently, okay? So the whole concept of segmentation is then that X is an unobserved field which contains discrete value pixels, and then Y is your observed data. And this is a little bit like a hidden Markov model, where at each location, Y can be a feature vector, not just a scalar. I mean, it could be a scalar, but it could also be a feature vector, and the feature vector can be extracted by using, what you can do is, if you have an image, you have you can have a little sliding window, and each window you extract some information, right? And based upon that information, you form a vector, okay, of dimension P, where you have P features that describe what's going on in that window. So now what happens is that at every pixel you have a vector, and the vectors are correlated clearly because they're formed from the same data. If the windows overlap, then they have overlapping information they're using to form the vectors. But you ignore that. I mean, it's an approximation, but you can just ignore that. This would be a typical mechanism by which you would do segmentation of a image spatially, right? And so then, if you have that kind of model, then the conditional distribution of all the data Y, given the classes X, is going to have what's sometimes referred to as a product form. So it's the product with the conditional probability of each observation, scalar, or vector at the pixel multiplied together. So here we say that the Y's are conditionally independent given the X's, right? So they're not independent because the X's could be dependent. So if you have, whenever you have a model like this, so you have, this is X. This is just like a hidden Markov model, by the way. So over here, this is a random field X, and then for each X, there's an associated Y. Right? So we say that the Y's are conditionally independent given the X, because if I take the nodes out with the X's, then all these Y's look independent. So what that means is if I know X, then the conditional distribution of the Y has a product form. Right? So that's called conditionally independent. That's just like what we have for a Markov model. Okay, and in that case, then you can take the log of the whole thing, and I found my first error. Okay, so this product here is supposed to be a sum, right? Because we're now, if I take the log of the product, it turns into a sum, and this log expression here is the log of the individual term. So this L of xs is what I'm calling the negative log likelihood. Okay? And so then the question is, well, we can pick any distribution we want for the conditional distribution of the YF given X. And often what we'll do is you can pick some sort of parametric distribution like Gaussian or Poisson or gamma or anything you want. And then you have, if it's like say Gaussian, then you can specify the distribution for each class by this mean and variance. So you're going to have like a parameter phi, okay, of m, and in this case, say if it's Gaussian, then phi of m would equal mu of m and sigma squared of m. Okay, but if it's some other distribution, it would be a few other parameters. So the phi there represents the conditional. It represents parameters that specify the distribution of the data given the x, okay? By the way, I generally use the letter c. Whenever you have the probability of y given x, if there's some parameters, I use the letter c for that. And if I have a probability of x, if there are parameters in that case, I use the letter theta. So theta are the parameters of the prior distribution. This is the prior. This is the convention I use. Okay, and c is the conditional distribution, is the parameter of the what I call the system. This is the system model, okay, or the forward model. Maybe is a better word. The forward model, okay. This is the prior model. This is the forward model, okay. And both of them might have parameters. So here, if each class is a different Gaussian distribution, it's specified by the parameters of the Gaussian distribution, which would be the mean and the variance. Or if it's multivariate Gaussian, then it might be it would be the mean vector and the covariance, okay? And if it's Gaussian mixture, it would even be more complicated because it would be all the parameters of the mixture. So it can be any distribution you want, okay? But but the important thing here is that c sub n is the parameters of the nth case. So what's going to end up happening is the conditional distribution of y of s, okay, at some pixel s, is going to be basically the conditional distribution of that for some parameter c, where c is the parameter that's relevant at that position. So the parameter that's relevant at that position is c of x sub s. But x is the class, right? So the class is then indexing c. So does this make sense? This is just like what we had for the hidden Markov model. That you have c of n such that n equals x of s. Because x of s is the class of that pixel. So if like the class is 2, then you pick parameter set 2. So now the problem of modeling the data just becomes one of picking this vector phi. So phi, the entire phi is going to be like p0, p1, up to c n minus 1, where there are n classes, right? Okay. So any questions about that? So that's basically what this looks like. So you have a bunch of p's. You select the phi associated with the class x, and that becomes the conditional distribution of y given x. And then if you have and then you can have more complicated distributions. I give an example here where we use a Gaussian mixture. So each class could be a Gaussian mixture. Why would you pick a Gaussian mixture? Well, because you can model any distribution to some level of accuracy with a Gaussian mixture. If you put more mixture components, you can model. If you have enough mixture components, you can model any distribution accurately with a Gaussian mixture. But you may need so many mixture components that it becomes not practical. But nonetheless, that's a justification for using Gaussian mixtures because they're flexible. So there's a lot of different things you could do. Okay. And here it just shows, this would be the distribution you have if you had a Gaussian mixture, equation 12.3. And this is the negative log likelihood. Okay. So now, once you have a model, so this is your model. You have a conditional distribution of the data, of the observations given on the latent image, the latent class. And then you have some distribution of the class. I mean, we haven't talked about that yet. Well, we're going to have some distribution for the class. Hold on. Let's see. okay, well this is going to be a Markov random field, okay? So we're going to assume that this thing's a Markov random field with discrete classes. So now, well, there's different things now we have to pick an estimator. Okay, we've been using the map estimator, so we can continue using the map estimator. In the map estimator, the cost is given by 1 if the two things don't match, and 0 if they do match. Okay. So then the optimal estimator is x. Okay. So we went through this before. The map estimate is going to then be the value of x, which maximizes the posterior probability, which is just the solution to the equation 12.5. Okay. Now, so that's fine. But the problem with the map estimator is that the criteria is kind of, ridiculous, actually. I mean, because it's saying, okay, so you have this 10 gigapixel image, okay? And it's saying if you get 1 pixel wrong, it's as bad as getting everything, okay? Well, I mean, that's silly. I mean, if you just had 1 pixel wrong, you'd be, like, delighted. That would be, like, a fantastic segmentation. You'd be extremely happy, okay? So this idea of being so insistent that every pixel be correct, it's like all or nothing, okay? It's like, give me liberty or give me death. I mean, I'd rather remain alive and be free, okay? It's a false choice. Well, it's a self-imposed false choice, okay? So instead, you'd say, well, here, a more reasonable criteria is to say, well, I'll sum, okay, the cost will be the number of misclassified pixels. That's more reasonable, right? You say, yeah, if I had 10 misclassified pixels, that's twice as bad as if I had 5. Okay? So if you do that, then you get what's called the MPM estimator, or the maximizer of the posterior marginals, because it can be easily shown that the estimator that minimizes this cost is the one that it's where you pick each pixel in equation 12.6. You pick each pixel to maximize the posterior probability of that pixel's classification given y. And you say, well, what's the difference between that and the map estimator? It looks like almost the same. So here's the map estimator here. Okay, it's the probability of x given y, where x is the whole random field. And this is the probability of xf given y. What's the difference between the map estimator and the NPM estimator?
Counting the errors.
Excuse me?
Counting the errors.
Well, that's one difference. That's the difference in the cost function. The map estimator just says all or nothing, and this one counts. But the actual, the result of, so the minimum mean square, okay, the minimum mean square error estimate is the conditional expectation, right? So one is the criteria, the other one is the result. So this is the result, equation 12.6. How does the resulting estimator differ for the NPM and the map? Because they almost look the same. You're maximizing over x, p of x given y here, that's the map. And here you have p of xf given y. What's the difference? They look the same.
Picking pixels individually.
Because here I'm maximizing the posterior probability of the individual pixel given all the data. And you say, well, that sounds even easier, because this is a vector x. I have to maximize over a vector x here for the map estimate, and for the NPM estimate, it's really easy. I just have this one pixel, and it only takes on, 4 classes, so I just have to check those 4 numbers and pick the maximum. So why is this hard?
We're going to calculate the marginal distribution.
Yeah, right, because the problem is you have to actually calculate the marginal distribution. So what do you have to do to calculate the marginal distribution for xf given y?
Integrate over all.
You got to integrate over all the other variables, which means you have to perform a sum over, if there's n states, right? You have to if there are n classes, you have to do a sum over n to the n minus 1. Because you have to sum over every other pixel. That's a ridiculously huge number of additions, okay? So that's not feasible. And in fact, you have to do that for every classified pixel. So you really have to do that times n. Of course, who cares? I mean, n to the n minus 1 is so huge. Why not just multiply by n? It's like the difference between now to the end of the universe and now to the end of the universe times 10 or something, or 100. It's basically ridiculous, no matter how you cut it. So you say, well, that's kind of a non-starter. Well, that was sort of a nice idea, but I guess it's not going to work. Well, we're going to come back to that, because there's ways you can approximately calculate the NPM estimator. So, and then 12.7 is just a representation of what you have to do here, which is that you have to compute an expectation over these variables, XR, that you don't want, basically. So, okay. Now, discrete optimization. So how do you solve this problem? Well, first of all, we talked about math. We talked about discrete Markov random fields, right? So discrete Markov random fields, the energy function is going to have the form of, well, it could have a lot of different forms, but this is a common one we've used at the bottom of page 269. Okay, well, you don't have this anyway, so it doesn't matter what the number of the pages. But you take the delta function, so you count, you add 1 for any pair of pixels which are of different class, neighboring pixels that are of different class. So that means the energy goes up as neighboring pixels, as there's more neighboring pixels of different classes. This is just like the ID model, but it's generalized to n classes, and it allows for having neighbors which are not just 4-point neighbors. You can have a larger neighborhood. So, so this is going to be the log prior distribution, and so then the map estimate is going to be the minimum over x of the sum of these two terms, right? Which is the minimum over x of the sum over x of the log of yf given access. And, okay, so this is the data term, and this is the prior term, okay? So, so now you just want to minimize that. Now this looks a lot, this equation 12.8, this looks a lot like what we had in, for the Markov model, right? When we were trying to do state sequence estimation, how did we solve the minimization problem for the Markov model when we wanted to do state estimation, maximum likelihood state estimation, or map state estimation? Does anybody remember how we did that? Okay, so let's go back in the Wayback Machine. Does anybody remember what the Wayback Machine is? It was a TV show when I was a kid. And it's called Fracture the Fairy Tale. And they had a thing called, they had Mr. Peabody, Mr. Peabody, and his boy, Sherman. So it was like a dog, okay? And the dog had a boy. The dog's name was Mr. Peabody, and he was a very scientific kind of guy. You could probably Google him right now and come up. And they had a machine and you said walk into the machine, and it was called the Wayback Machine. Okay. And because it took you way back. I don't know what this has to do with anything, but I can't any story. It took you way back in time, and he goes visit like the dinosaurs and the Romans and various things like that with his boy Sherman. Anyway, so taking the Wayback Machine back to, I don't know, 10 lectures ago, the hidden Markov model. Does anybody remember hidden Markov models? HMM. Hidden Markov models. Does anybody recall those in their deepest, vaguest memory? Someone make me feel good, please. I entertained you with the Wayback Machine. Come on, guys. Tell me a break here. The HMM, do you remember it? Yes. Say yes. Say it with gusto. The HMM. Okay, now, you had an HMM, right? You had a discrete state that evolved in time. And in each time, you had an observed, say, continuous, it could be discrete too. You had a continuous variable that you observed, like Gaussian. It was conditionally Gaussian given the state, right? Do you remember that? It was the same equation you had to minimize in order to find the map estimate. So this is x and this is y. But if you wanted to find p of x given y, you wanted to maximize this over x, that's x hat. That's the maximum map sequence estimation. Remember we did map sequence estimation? Do you remember that? Okay. So now, why do you do map sequence estimation? Was there a reason? Was it just to torture people in the class, or what was the map sequence estimation for? Do you remember what a hidden Markov model is for? What kind of thing might you apply to? Give me like any application where it might work. Speech. Okay, speech recognition. There you go. And then the state would represent something like what? Might represent like
the actual meanings of the words.
It could represent the meanings of the words, okay? It could actually be the words. What else could it be? It starts with a PH.
Phonemes.
Phonemes. It could represent the phonemes, okay? Because you have a finite number of phoneme classes, and then whichever phoneme is being expressed at that time, okay? That's the class state you'd estimate, right? Now, this can also be used in applications. It's a little different, but it's very similar. When you're doing maximum likelihood sequence decoding in modems, okay? So that would be like how your cell phone works. It actually does this. It has, okay? So how do you find the optimum solution? It was a technique we used, and it starts with a D. You use dynamic programming. Great. See, I knew you had it in it, didn't you? You use dynamic programming. Can you use dynamic programming to solve this problem here in equation 12.8 in 2 dimensions? Come on, guys. Can you use dynamic programming? In 2D? So what's the difference? Here is 1D, right? In 2D, we have to find the state, but instead, we have a situation like that, like this. We have an array of states that are discrete. Right? But now, for each state, we also have a little observation. Does everybody understand what I'm drawing here? Does anybody understand what I'm drawing here? Does anybody want to ask a question about what I'm drawing here? Finish drawing it. Does that make sense? What does it mean? So what are these little things there? Those are observations, and this is what? So what? It's an X, which is like it's the prior model, and in particular, it has what characteristic? It's not continuous. What's the opposite of continuous?
Discrete.
It's discrete, right? Because it takes on discrete values, right? Like 0 through 4. Okay? And then we have 5 values, right? It's important that it's discrete, because you can't do this dynamic programming on if it's continuous. Dynamic programming requires that you actually enumerate the discrete state. If it's continuous, it can't be done. You could approximate it, you could bin the continuous variable up into the discrete state, but you can't do it if it's truly just continuous. Okay? So this is discrete, okay? It's analogous to this in 1D, but here you just have a 1D connection, right, in an observation. Here you have 2D. So now, the X is just like an Ising model, okay? We talked about Ising model. Now, if you want to calculate the map estimate, this state here depends on its 4 neighboring states and the observation, right? Can we do a global minimization of this X? So we have P of Y given X times P of X. Can we do a global maximization with respect to X? Yes, no, maybe so? If you don't know the answer, why don't you just think about it out loud with me?
So in principle, it seems like you could do dynamic programming if it's like discrete stuff.
It seems like you might be able to do dynamic programming. How would you set up the dynamic programming problem?
Well, it's a lot more complicated than regular case.
It's more complicated than the regular case. What's the key to dynamic programming? Does anybody remember dynamic programming? A little bit. You work what way?
So you go back and forth.
Yeah, you go back and forth, but mostly you start off going backwards. You go backwards. Like dynamic programming, usually the way people think about it is that you work backwards. So dynamic programming is like what you intuitively do. If you know that, like next week I have to be in Boston on Thursday, right? I'll say, okay, what time do I have to be in Boston? I know I have to be there at 5 p.m., which means my flight, I have to find a flight that arrives at 5, and that flight, you know, the best flight departs at 9 a.m., which means that I have to wake up 2.5 hours early. I have to leave 2.5 hours early, you know. So if it's 8, so it's 5:30, which means I have to wake up an hour before that to take my shower, which means I have to, you know, I work backwards, all the things I have to accomplish in order to be able to be at that point at the specified time, right? That's sort of dynamic programming. You work backwards, okay, to figure out where you need to be. So, so in this problem, you start off with the last stage, and you kind of work backwards in dynamic programming in 1D. The problem in 2D is that, well, I could set this as a 1D program. I can actually make every row of the image a single state. The problem is if I do that, and let's say this is, let's say this is an n-pixel image, then the number of elements in a row will be the square root of n, right? And so I have n to the square root of n possible states for a single row, because every one of these things can be in n different states, and there's square root of n of them, okay? So the dynamic programming problem has exponential complexity because each state of a single row itself has an exponential number of states, okay? So this is not practical. You might think what you'd be able to do is maybe set up some kind of raster order thing, okay? Where you do this one and somehow chain this up along, but it doesn't work. I mean, people have screwed around with this for a long time, trying to figure out how to set up a 2D dynamic programming problem. And you can get something approximate by, say, looking ahead a few rows, okay? But you can't do it exactly. And you can do approximate methods, and sometimes they're useful. So the bottom line is that you can't solve this with dynamic programming. Okay? Now, so you say, oh, well, I guess you can't do it. Interestingly, you can do it under certain cases, and in fact, there's been a lot of interest in this over the years because it's pretty effective for some kinds of problems. And I pointed you to some references here. How many people have taken like 608? Maybe you cover this in 608. You use the Ford-Fulkerson algorithm in 608? Okay, so the Ford-Fulkerson algorithm is like a classic algorithm. It's a graph cut algorithm based upon the max flow min cut theory. Okay? So basically what happens is that if you can set up your graph in a way that if the graph has binary, if the states of the graph is binary values, so in this case n has to equal 2. If n equals 2, then you can solve any problem of this form optimally in polynomial time using the Ford-Fulkerson algorithm. And you can get code on the web for doing this. It's become pretty popular now. So this is a significant practical technique which people really use, but it has limitations. One limitation is that it doesn't work for n greater than 2. That's not too bad because what you can do is you can set up your segmentation problem so you first separate into 2 classes and then separate the remaining classes into 2 classes. So you can do like a binary segmentation, okay? It's not optimal, you lose something, but it's okay. But the thing that really messes this method up is that if your forward model, and I know we're not doing this here, but if your forward model has the form y minus ax, then it totally screws up the Ford-Fulkerson algorithm because it causes cross-coupling between the terms, the binary terms. So you basically can't use it in that case. So the Ford-Fulkerson algorithm is popular, it's used, it's effective, it can be fast, it's properly implemented. I mean, I don't know that they actually use, I'm not an expert on this, so I don't know that they actually use the Ford-Fulkerson algorithm, which is probably the original algorithm. There's probably variants on it that are faster or whatever. But the methodology can be solved in polynomial time, it's practical, but it has limitations, okay? We won't talk about that very much. So the method, so then the question is, well, what if you can't use the Ford-Fulkerson algorithm or graph cut algorithm? How do you do this minimization, okay? Well, one way to do it is just to do local updates, like we did ICD. Here what you can do is you can do updating of an individual class of individual pixels and they call that ICM. iterated conditional modes. I'll tell you in just a minute why they call it. It's called the iterated conditional mode because you think of it as the conditional distribution of a single pixel's class given all the other pixels. Okay. So you can say you're maximizing the mode of the distribution. Okay. Yeah. But essentially what you're doing is you're minimizing this cost function with respect to a single pixel. So it's just like ICD that you implemented for lab 2, right? Or lab 1. Lab 1, okay? And you're going to implement for lab 3, right? Or you have implemented for lab 3. So you do iterated. Now every time you update a pixel, so is this sequence of operations that update these pixels, is it guaranteed? So this is the this is iterated conditional mode. Because if you compute the conditional distribution, if you minimize the conditional distribution, oh, this is a mistake. That's what max. Yeah, I'm finding errors in my desk. Okay, if you maximize the conditional distribution of a single pixel given all the other, all the rest of the data and all the other pixels, then that's equivalent to, you can just go through these steps and you can show that it's equivalent to minimizing this cost function that I was just talking about with respect to a single pixel discrete state. So, now, is this algorithm, so that's why it's called iterated conditional modes, because this thing here is a mode. It's the mode of the conditional distribution. You've heard of that term, mode. So if you have a distribution and you have something like this, this is called the mode of the distribution because it's the local peak. Okay? Now, if you, okay, so now, is this iterated conditional mode algorithm guaranteed to converge? Yes, no, maybe so. Which is it? You're guessing a no. Are there any guesses of yes? By the way, any answer here is correct. Okay. Depending upon, because my question isn't actually very well formulated. So you can reformulate my question to make whatever answer you give true. Okay. So does somebody else want to say yes? It does converge? And does somebody else want to say maybe? So you guys can give me the question to the answer instead of the answer to the question. It could be either like Jeopardy or Hitchhiker's Guide to the Galaxy, depending upon your viewpoint. Okay. So, why would it converge? No fair looking down at your paper. Anybody who looks down at their good paper is going to get called on. You have to look at me attentively. Oh, come on, guys. Okay. If I have a hill here, okay? Okay, and I take a bowling ball, okay? Will the bowling ball eventually stop? How many people think the bowling ball will keep rolling to infinity? Okay, everybody who thinks the bowling ball will roll forever, put up your hand. Okay, good. Otherwise, I wouldn't go bowling with anybody who answered that question. Okay, how many people think the bowling ball is going to eventually stop rolling? Okay, thank goodness. Okay, now all people who have no physical intuition whatsoever and have never experienced a bowling ball. Do you know what a bowling ball is, by the way? You know, it's like that thing that's round like this and it has 3 holes in it, like this. And you put your fingers in it and you roll it and then it knocks these pins over. You play this game with it. You've done this before, right? Okay, so the bowling ball's going to roll down the hill, right? And what's going to happen? By the way, there really can't be a wrong answer. Come on. Just give me any answer. Please. Give me something. If I let go of the bowling ball, I know you're all very shy. Okay? But if I let go of the bowling ball, what's going to happen? Come on, please.
It'll stop somewhere.
It'll stop somewhere.
Just stop there.
Yeah, it depends how high of the hill it is.
It's going to stop. I mean, actually, if it's a really smooth hill, like a glass hill, okay? It's a really good bowling ball, it'll roll like a roller coaster and come down here, okay? But eventually, it's not going to go above there because that's higher, okay? And so it'll keep rolling back and forth. It'll end up somewhere. It'll either end up here or it'll end up here, right? Okay. Now, okay, good. So why is it you know that the bowling ball converges? I want you to just learn this one concept, okay? This is perhaps one of the most important concepts we've learned in the entire class, guys. If you have an algorithm which reduces the energy of the system, the height, say the height of the bowling ball, with every step, okay? Well, the energy of the bowling ball is a combination of its height plus kinetic energy, right? In every step, is it possible for the bowling ball's energy to go up? Is it a rocket-propelled bowling ball? No. Okay? So there's no energy being put into the system, right? So with every step of time, the energy does what?
Goes down.
It has to go down or stay the same. Okay? So as the energy goes down, what do you know? Eventually it has to what?
Stop going down.
It has to stop going down because it can't go down to minus infinity. Okay? There's not like an abyss here where it can fall to the center of the earth, okay? So it has, it has to converge because every step the energy goes down until it reaches some local minimum, right? So every time I update a pixel here with the class, I produce a better class for a pixel, what happens to the energy?
It goes down.
It goes down. And can it go down to minus infinity? Why? Because all the terms are positive, right? So this thing's bounded below. So with every step, the energy goes down. And if the energy goes down with every step, eventually something's got to give. It's got to stop. Okay? So what does that tell you? It converges. Now, actually, it doesn't have to converge for the following slightly twisted reason, okay? Because I can have a flat region here, a perfectly flat region, and the bowling ball could just keep bouncing back and forth, like that, okay? But that's really, not in the spirit of the whole thing, okay? So if I have two states that have exactly the same energy, I could just keep going back and forth between them. But as long as I have a rule-breaking thing, I just say, okay, I only change the state when the energy strictly decreases. Then I'm guaranteed to converge. Okay? Okay. Now, good. Okay, so this is now the ICM algorithm. You just keep replacing pixels with the value of the pixel that minimizes the cost, right? And you only have to check the neighboring pixels so it's efficient to implement, because the cost is only a function of neighboring pixels when you update one pixel. So you guys are going to understand this, and you're going to implement it in Lab 3, correct? Now, so now there's an interesting thing. Now the problem is though, you can get stuck in local minimums. So, what will end up happening, you'll see, is that you get stuck in positions like this, where you're not at the global minimum. So, how do you get closer to the global minimum? Oh, we're out of time. For that, you can use simulated annealing, okay? Or you can use another method. You're going to read these sections, okay? Or you can use next time we'll talk about stochastic NPN, okay? That's another way of generating a result where you sample from the posterior. So, good. It's been good seeing you today. Bye. Oh, that was it for the whole semester.